organic chemistry, saturated hydrocarbons. That's what we start talking about. Okay. Organic chemistry is the chemistry of carbon. Okay. Carbon forms stable covalent bonds with other carbon atoms. Okay. Carbon forms a chain. Okay. Carbon forms up to 4 covalent bonds with other covalent atoms. Okay. Remember Lewis structures. Carbon has 4 valence electrons. And we do our Lewis structures, we know that everything has the octet rule. They want to have 8. So if you bond to hydrogen, which has 1, hydrogen which has 1, hydrogen which has 1, and another hydrogen which has 1, that's CH4. That's methane gas. Okay? That's the simplest hydrocarbon. Okay? It's 1 carbon. So carbon can bond to hydrogen, and it can bond to other elements. It can bond to oxygen. It can form single bonds with oxygen or double bonds with oxygen, depending on the structure. It bonds to nitrogen. It can form a single bond to nitrogen, a double bond, or a triple bond with nitrogen. Okay. Remember when we did Lewis structures, if we did, let's say, hydrogen cyanide, HCN, okay, we count the valence electrons and we balance our structures. That's so we know how these things form and the shapes are going to take on. So let's take on hydrogen has 1, carbon has 4, nitrogen has 5. They're valence electrons for a total of 10. So you put carbon, bonds to nitrogen, bonds to hydrogen. That's your structure. Now you got to make that have 10 valence electrons. Right now that is way too many. So in this case, carbon would form a triple bond with nitrogen and there'd be 2 electrons there. Remember, every bond is 2 electrons. So there's 2, 4, 6, 8, there's 10. That's the structure of hydrogen cyanide, a triple bond between carbon and nitrogen. Right? Methane is single bonds between the carbon and the hydrogens. And if you remember the VSEPR rules, the valence shell electron pair repulsion, you can predict the shapes. The shapes are going to be really important. In organic chemistry, especially biochemistry, all of our enzymes, all of our neurotransmitters, everything in the body binds by shape. Okay, that's how we recognize certain things. I mean, take the body doesn't produce heroin or produce morphine, but it works in our bodies because it mimics the shape of a natural occurring, in this case, a neurotransmitter, and it stimulates dopamine in the body. Okay, so everything works by shape. The shape here around this carbon atom is linear. That's 180 degrees. Okay, because there's the same direction of force in both directions. Remember that these all electrons are negative. So they're going to repel each other because like charges repel to get furthest away. The furthest they can get is 180 degrees. In this compound here in methane, okay, there's 4 bonds to the carbon. This is what's called a tetrahedral. And every angle is 109.5 degrees. That's the angle that everything bends in 3 dimensions to make it the furthest away from each bond. Because every bond is negative. Because a bond is 2 electrons. It's 4 electrons in a double bond, 6 electrons in a triple bond. Okay? But they're always negative because electrons are negative. So they repel one another and they take on certain shapes. Okay? So oxygen can have up to 2 bonds with carbon. Nitrogen can have up to 3 bonds. Sulfur can have up to 2 bonds. And halogens can only have 1 bond. Remember, if you remember the rules of Lewis structures, hydrogens and halogens are always terminal. Okay, once they hit that, they cannot have any other bonds. So if you've got a carbon atom, you can bond to another carbon atom. If you come into a chlorine or any other halogen, this stops. That chlorine can have no other bonds. The carbon can keep going, but you can't bond anything else to the chlorine. Because if the halogens were in the periodic table, they have 7 valence electrons. So once they make that 1 extra one, they have 8, and that's it. Everything wants to follow the octet rule. Okay? So if you remember that hydrogen and the halogens are terminal. Carbons can keep bonding along. Okay? Oxygen can keep bonding along. Okay? Nitrogen can do the same thing. But the hydrogen and halogens are terminal. Once they reach that, they stop They stop the bonds. You only have one bond attached to your halogen. So that's a terminal group. Same with the hydrogen. These hydrogen here, once you reach hydrogen, it cannot have any more bonds to it. Okay? Now, the presence of all these elements gives it different physical properties and different chemical properties for organic compounds. So we have a ton, hundreds of thousands of organic compounds because carbon can combine with so many different elements and in so many different forms, so many different ways. Okay, carbon has 3 allotropic forms. Okay, allotropic is the basic forms of carbon. It can be a graphite in planar layers. In other words, set across one plane. That's the most stable form of carbon. There's no stress. It all forms in one plane. A diamond is the other form carbon can take on. And that's a 3-dimensional network. Okay? Those are tetrahedral structures at each carbon atom. And we have a new one called Buckminster fullerenes. Buckminster was an architect who designed these geodesic domes for houses. You ever see them in the desert? There's round geodesic houses. Those are Buckminster Fuller homes. And they named this after him. And it's 60 carbons in what's like a soccer ball. Okay? I think I have a picture of it here too. Yeah. So you have 60 carbons arranged in the soccer ball form. You have the graphite, which is in straight lines. And then you have the diamond, which everything is a tetrahedral. So in this one, you have a carbon, bonded to carbon, bonded to carbon, bonded to carbon, bonded to carbon, and so on. It repeats itself. And each of these is 109.5 degrees, a tetrahedral shape. Okay? So it puts stress on the structure. This is a ball of 60-degree carbon. They ended up discovering this with one of the space missions, and how carbon can do this from one of our missions there. And it's a really neat idea because if you can form a ball of something, now we can use that in the body to determine and deliver different drugs. Like AZT for AIDS treatment was put inside of these Buckminster fullerenes and delivered to different tissues. And we could get it at different places by using it and manipulating the shape of these carbon atoms. So it plays a vital role in medicine and everything else that we do. The most stable form of carbon is graphite. There's no stress on it. There's single planar layers. There's no stress on the carbon. Okay. So if you really want to give your girlfriend or your wife a ring that lasts forever, you give them one made from graphite, not from diamond. Don't say I said that, I'll get in really big trouble for that. My wife didn't buy that either, so. All right, so carbon can take on those basic elemental shapes, those 3 shapes. Graphite, which is linear. Diamond, which is 109.5 degrees tetrahedral form. And then Buckminster fullerene, which is like a soccer ball. And all that is these 6 pointed figures, like hexagonal shapes, all matched together. Okay, we'll go with because different rings of carbon will have different shapes, but basically these Buckminster fullerenes are like hexagons, and then they line up with one another. Okay, and so on and so on, and repeats in shapes of 60. All right, so why are there so many organic compounds? Okay, carbon atoms can form double or triple bonds along with single bonds. Like I said, it can produce hundreds of thousands of different structures. So carbon can have a double bond between 2 carbon atoms. Carbon can have a triple bond between 2 carbon atoms. Okay? Carbon can form double or triple bonds with other components. This is hydrogen cyanide, which you just showed an example of. Carbon has a triple bond, or this is acetone. Carbon can have a double bond to oxygen also. So because of its ability to have 4 different bonds to it and be stable, carbon can form multiple compounds. And that's what gives it all the different compounds that we can use. That's why the designer drugs are possible, because we can take this carbon and bring it all around. Okay. The number of ways to arrange carbon atoms is limitless. You can arrange carbon atoms all kinds of different directions. And the more you have, the more possibilities there are for arranging them. Okay. You can have branched chains of carbon. You know, the carbon can come across. You can have a straight line of carbon atoms. You can branch carbon atoms. They can have branches all over the place. Okay. Carbon can have a ring structure. Okay. where they bond to each other, just like in the Buckminster fullerenes. Okay, so carbon can be straight, linear chains. It can branch, or it can form rings, and it can form with multiple numbers. You have cyclooctane, which is 8 carbons in a ring. Cyclohexane is 6 carbons in a ring. Cyclobutane is 4 carbons in a ring. So it can make multiple rings, multiple formations, multiple rings, branches. And we have to be able to name all these compounds so we identify them. Every single organic compound we have to be able to give a unique name to. So when we put it in text or put it in print, we can mimic that molecular shape of what it is. So we have to give it, everything has to have a unique name. So 2 organic compounds even have the same number and kind of atoms, but completely different structures. That's what is called an isomer. Okay. So isomers by definition, okay, same molecular structure, same molecular compound, same chemical compound. So if it's C4H10, it's C4H10, but different chemical structure. So it's the same compound, but different structure. It's drawn differently. Okay. So isomers are a big part of organic chemistry. Okay. A lot of carbon compounds exist in these different isomers. So it's the same molecular formula, different structural formula. So it's got the same number of carbon atoms, same number of hydrogen atoms, same number of chlorine, whatever else is in it. It's all the same, but they're arranged differently. It's a different shape. And if it's a different shape, it's a different name. We name them differently. So remember, isomer, same molecular formula, different structural formula. Okay, let's just for example, C4H10. So if you look at that chemical compound, we know how many carbon atoms are in it. 4, right? Okay. How many hydrogen atoms are in it?
10.
10, perfect. But you can have different structures. So it's the same same molecular formula, different structural formula. Okay, butane is 4 carbons all in a row. That's butane. Count the number of carbons, count the number of hydrogens. There's C4, H10. Okay, 2-methylpropane is still C4H10, and this is carbon, 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 carbon. And this is CH3, and these are hydrogens. Because every carbon has to have 4 attachments. Okay. So this one's straight line. This one is branched, but this is still C4H10. There's 4 carbons, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. Okay. So it's the same chemical formula, different structure. So it has different names. Like I said, and you'll learn how to name these tonight too. This is butane, and this one here is 2-methylpropane. Same molecular formula, okay, but a different structure. If it's a different structure, it's got a different name because it's going to have a different function. Okay, butane is lighter fluid for cigarette lighters. Okay? 2-methylpropane is not going to burn a cigarette lighter. Okay, different chemical properties. So each of those compounds has the same. Okay, each compound has the same molecular formula as C4H10. Let's do C4H10 here. Okay, each one of these. Here is linear with a double bond. Here it's linear with a double bond. And this is the ring structure. Okay. You look at the first one. If we number our carbons, 1, 2, 3, and 4. Number these ones, 1, 2, 3, and 4. Look at the position of the double bond. In the top compound, the double bond is applied to the number 1 carbon. In the second compound, the double bond is at the number 2 carbon. Different structure. It's going to have different shape, different function. It's going to have a different name. Okay. The top one is butene. The second one here is 2-butene. So this is butene. And this one here down here is 2-butene. Now look at the third one down. These are 4 carbons, all in a circle. Okay. Every carbon is counted, and count the hydrogens, 2, 4, 6, 8. Every one of those is C4H8. All 3 of those have the same chemical formula, but very different structural formulas. Okay. So you notice in all these compounds that we're dealing with, whenever we do organic chemistry, every carbon atom has to have 4 bonds to it, or it's not stable. So every carbon atom needs 4 bonds. Check all the compounds up above. You will look at all of them. You'll see every carbon has 4 bonds to it. Okay, so those are isomers. Same chemical formula, different structural formula. Okay, there's difference between organic and inorganic compounds. Organic compounds have covalent bonds. They share the electrons in the bonds. Inorganic compounds usually have what's called ionic bonds. They transfer electrons. Take a simple example, sodium chloride. Sodium has 1 valence electron. Chlorine has 7 valence electrons. Okay. What happens is this electron here goes to chlorine, giving you Na plus and Cl minus. Because again, electrons have a negative charge. Okay, so that gives you a negative charge to it. So then you have sodium chloride, and then there's a positive charge and a negative charge. What do opposite charges do? Do they repel or attract? Got it? Okay. Similar charges repel, right? Similar charges repel, opposite charges attract. So these are opposite charges. So now we have a bond that pulls those together. That's an ionic bond because there's opposite charges and they're pulled together. Those usually form crystals and very strong inorganic compounds. Okay, so the big difference between organic and inorganic. Organic is covalent bonds where they share the electrons. Inorganic is polar bonds where electrons are transferred, actually given from one to another, creating opposite charges, and that pulls them together. So far, so good. That's a little review from general chemistry. So organic compounds are molecules. They don't form crystals. Okay, because they're not held together by charges. And they're non-electrolytes. They are not polar. Okay, inorganic compounds, because they have these positive and negative charges, so you got a positive charge, negative, 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 negative around it, positive, negative, negative, negative around it. Okay, that's how these charges bond. They form these 3-dimensional crystal structures. Okay, they're often water soluble. Okay, when you put salt in water and stir it, what happens? Table salt. It dissolves, right? Because water is polar. Water has positive and negative charges. Okay, and it allows for the charges to disassociate and bond with water. That's where things will dissolve. That's where the formula like dissolves like comes from. So polar will dissolve into a polar compound. Polar compounds will dissolve in a polar medium. Non-polar compounds will dissolve in a non-polar medium. Okay. So you remember water is polar, even though water is molecular, because there's water, right? Oxygen is very electronegative, so it pulls electrons towards it, giving that a negative charge, giving that a small positive charge. Okay? So therefore, if you have polar charges like you do with water, that can dissolve the inorganic compounds. So inorganic compounds dissolve in water, organic compounds do not. Okay? Because organic compounds are molecules, they're non-electrolytes. Then compare melting and boiling points. Organic compounds have much lower melting points Then inorganic compounds. Inorganic form those three-dimensional crystals. Okay? Your intermolecular forces are broken fairly easily in organic compounds. Intermolecular means the forces between molecules. When you see intramolecular, those are the forces within the molecule. Okay? So the intermolecular forces are the forces between molecules. So if we have water and bonds to another water, okay, bonds to another water. That's that hydrogen bond. Those are just forces. These are the forces between molecules. That's your intermolecular forces. Those ones broken fairly easily. The intramolecular forces are the ones inside the molecule. Those are very hard to break. So the intermolecular forces are broken fairly easily in organic compounds, giving them lower melting points than inorganic compounds. Inorganics have higher melting points than organic compounds because they form a crystalline structure. They have those positive and negative charges really holding them together. Whereas organic compounds do not have that.
I had a quick question.
Sure.
So you said inter was between the forces between molecules,
Between molecules.
and intra was what? Sorry.
Intra is within the molecule itself. In other words, if we had methane, we had CH4, right? That was our methane gas, carbon and 4 hydrogen. Now there's an attractive force. There's CH4 again. There's a force between those molecules. Okay, there's shifts in electrons. There's what was called London dispersion forces in biology or other chemistry. Remember London dispersion forces? There's a force holding that together. This force can be easily broken, that bond. That is intermolecular. Intramolecular is this bond right here. This carbon-hydrogen bond, inside the molecule. This bond is very difficult to break, this carbon-hydrogen bond. Did that clear it up?
Yeah, it does. Thank you very much.
Yeah.
Okay, no problem. So that's the difference between intramolecular, between the molecules, intra, within the molecule. So the intramolecular bonds of here are oxygen, hydrogen, and water. Again, very difficult to break apart. Okay. So things that are soluble, polar compounds are water soluble because the rule is like dissolves like. Okay. Polar compounds dissolve in polar media like water. Non-polar molecules dissolve in non-polar media like hexane or octane. Okay. So organic compounds are non-polar, water insoluble. Inorganic compounds are water soluble and readily break apart. Okay. If you take gasoline, which is an organic compound, and you pour it in water, they don't mix, right? You take oil, you pour it in water, they don't mix. Because like dissolves like. Okay. So if you take the inorganic compounds like salts, potassium, sodium, chloride, they dissolve. They form what's called electrolytes, like in those energy drinks that you drink, Gatorade, Powerades. Okay, they're full of electrolytes. Okay, those are to help restore the body during exercise and things like that. Now, there is a danger with drinking those energy drinks, Gatorade, or if you freeze them. Okay, if you freeze them, what happens? The water freezes. The electrolytes don't. There's a 13-year-old kid in New Jersey, it's been about 6 years now. He was pitching a baseball game. Okay. Then near the end of the game, his parents brought him some frozen Gatorade. He drank the Gatorade and he died from it. Put his body into shock. It dropped all these electrolytes into his system without any water with it because it was frozen. So if you want to give your kids Gatorade and stuff, just make sure it's not frozen. Okay, because those electrolytes don't freeze with the water. The water freezes because of the intermolecular forces between water molecules, whereas the ions don't freeze. So comparison of major properties of organic and inorganic compounds. Molecular mass is just the weight. They're organic compound like butane or sodium chloride, very similar weights. Okay. The bonding is covalent for organic and ionic for inorganic. Remember, covalent shares, ionic compounds transfer electrons and are held by charges. The physical state, okay, is a gas at room temperature and a solid at room temperature. Okay? Because the intermolecular forces are so much greater with the ionic compounds, they pull together tighter and form a solid. There's not much holding butane together. There's the intermolecular forces are very weak. Those are your London dispersion forces. Boiling point, -5 degrees centigrade, 1,413 degrees centigrade. Much higher boiling point. Okay. Melting point is the same way, very low, extremely high. Okay. To break the bonds, the intermolecular force between butane molecules is easy. We can put it into a gas stage. To break the bonds of sodium chloride, it's extremely difficult. We got to really heat the salt up to break those bonds. Okay, solubility in water. Organic compounds are insoluble in water. Inorganic compounds are highly soluble in water. Remember, like dissolves like. Okay. Solubility in organic solvents is high. Okay, so organic compounds dissolve in organic solvents. Okay, inorganic compounds do not dissolve in organic solvents. Remember, the rule to remember is like dissolves like. Okay, flammability, organic compounds are very flammable. Gasoline, octane is a fuel. Kerosene is a fuel. Methane gas. Okay, butane, lighter fluids, propane. Those are all organic compounds. Those all explode when you light them. They're very flammable. Inorganic compounds are not flammable. Salt doesn't catch fire. You can melt it. It may make a mess, but it doesn't catch fire. It's not flammable. Okay. Electrical conductivity. Organic compounds are non-conductors. There's no charge. There's no electrons to move around. Inorganic compounds conduct electricity in solution. Okay. If you want to electrocute someone in a bathtub, plain water with no ions will not do anything. Add salt in the water, now you got a conductor. Now it will electrocute if you put an electrical appliance in the bathtub. Okay, because the salt has to be there for the ions to flow. Okay, so it conducts electricity. All right, here's two different compounds. This is ammonium cyanide. Okay, even though there's carbon here, okay, this is an inorganic compound. Okay, so just because it has carbon does not mean it's organic. Because this is carbon forming a complex, forms a negative charge and a positive charge. Ammonium cyanide. Okay, these are held together by positive charges. Okay, opposite charges attract one another. Okay, this is urea. This has carbon. This is an organic compound. Okay, all the bonds are molecular bonds. Okay, they're covalent. Everything's being shared. This is ionic. You have charges holding together. These are all shared bonds. Okay, does that make sense? So even though it has carbon, okay, it's not necessarily organic. If it forms a salt with carbon in it, it is an inorganic compound. If it's all molecular bonding, all covalent, then it's an organic compound. Okay. Question in the book. A student is pressed with a sample of unknown substance and asked to classify the substance as organic or inorganic. What test should the student carry out? What's an easy one? Drop it in what? Drop in water. If it dissolves, yeah, perfect. Drop in water. If it dissolves, it's inorganic. If it doesn't, could be organic. Get a melting point on it. Melting point very low for organic, very high for inorganic. So there's all kinds of different tests. You can do melting point. You can do the boiling point, solubility in water you talked about. Solubility in organic solvent, flammability, see if it burns, electroconductivity, okay, melting point if it's inorganic, okay, inorganic compound. Will melting point be high or low?
Low.
High.
We got a low and a high. It'll be very high because it's got those charges holding together. It's hard to melt. It's hard to break those intermolecular forces. Boiling point, high or low?
High.
High. Perfect. Solubility in water, yes or no for inorganic?
Yes.
Yes. Perfect. Solubility in organic solvent, yes or no for inorganic?
No.
Nope. Flammability, is it going to burn if it is inorganic?
No.
No, they don't burn. Okay, it's hard. They're held together with. And electroconductivity, will it conduct electricity if it is inorganic?
Yes.
Yes. If you dissolve in a liquid, it'll have ions that conduct electricity. So those are any of those tests you can do and just compare the results, and you can determine whether something is inorganic, inorganic. Okay. What results would you expect if the sample in question 10 were inorganic compound? Okay. So the melting point, we just went through this. The melting point for inorganic will be high. Melting point for organic will be low. Boiling point, inorganic was high, organic was low. Solubility in water, inorganic will be soluble in water because it has charges. Like dissolves like. Okay, so high soluble in water. Organic will not dissolve in water. It'll be low. Solubility in organic solvent for an inorganic compound will be very low. Again, like dissolves like. For an organic compound and an organic solvent, it's going to dissolve. It's going to be high. Flammability, inorganic compounds don't burn. Okay, flammability will be very low or no flammability. Organic compounds that burn readily. It'll be very flammable. Okay? So you can determine by these different tests whether you can be dealing with an organic or inorganic compound. Oh, electrical conductivity. For inorganic, definitely. It will conduct electricity. Organic compounds will not. So easy to tell them apart. All right, let's start talking about hydrocarbons. That's the backbone of chemistry. Hydrocarbons strictly means hydrogen and carbon. That's it. So hydrocarbons contain only hydrogen and carbon. They're non-polar molecules. Okay, there's nothing to make them polar. There's no electronegativity distance like water, oxygen, nitrogen, anything to give it a polar compound. It's only carbon and hydrogen. So they're not soluble in water because water is polar. They're soluble in typical non-polar organic solvents like toluene and pentane. These are non-polar solvents, so organic compounds will dissolve in those. Okay, this is toluene, which you're going to learn about in this chapter, how to name this. This is what's called a benzene ring with a CH3 group attached to it. That's toluene. And this is pentane. Pentane means, penta is like pentagon. Pentagon is how many sides?
5.
5. So penta is 5 carbons. 1, 2, 3, 4, 5. And the ANE ending means it's all single bonds. So we're going to determine how to name these things in just a second. So that's toluene, and this is pentane. And those are hydrocarbons. They're hydrocarbons, there's no polarity. They're non-polar compounds. Substituted hydrocarbons. Okay. Hydrocarbons are constructive chains and rings of carbon atoms with sufficient hydrogen atoms to fulfill carbon's need for 4 bonds. Okay. In other words, if you have 4 carbons, you're going to have a certain amount of hydrogen to make sure everything has 4 bonds. So every bond, every carbon has to have 4. So that's going to give you 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. Okay. So when you have your hydrocarbon chains or rings, you've got to have enough hydrogen to fill the needs for bonds. So if I have, let me give you a compound like this. Let's see, I need to make this a whiteboard. There you go. All right. There's your compound. You have 1, 2, 3, 4, 5, 6, 7 carbons. How many hydrogen would you have? Okay. Yep. How many?
16?
16. Perfect. You got it. You have 1, 2, 3, 4, 5, 6 carbons. You would have, no, how many carbons did I say I had? 1, 2, 3, 4, 5, 6, 7 carbons. Sorry. We have 7 carbons. And we would have 16 hydrogens. Okay. You'd have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay. So you have to have enough hydrogens to make every carbon have 4 bonds. That's what substituted means. They have to have enough hydrogens to make sure every carbon is going to have 4 attachments to it. Okay. If you have a substituted hydrocarbon, which means you're adding something, you're substituting one of the hydrogens. Okay. Put on a chlorine, put on an oxygen, put on a nitrogen. You're putting something in there that's going to replace one of the hydrogens. Now it's a substituted hydrocarbon. There's more than just carbon and hydrogen in it. I get my group here. All right. So methane. Remember what methane? Methane was the simplest hydrocarbon. 1 carbon, 4 hydrogens. Okay. But methane has some very unusual behaviors with it. Okay. Methane can form what's called clathrates. Okay. It's a type of matter in which molecules of one substance form a cage around molecules of another substance. We talked about it a little bit with the Buckminster Fullers, as we can form that cage around different drugs and deliver it to the body and get it to different places. We can control where that drug acts. So if a drug is very toxic to the body, like AZT for AIDS treatment, okay, we can get it there without infecting other tissues to where we need it to be. So it's an important medical concept also. But to form a cage around these different molecules with methane gas. So water molecules can form this like lattice work around methane molecules to form frozen what's called methane hydrate, which means it's methane with water. That's probably one of the biggest reserves of fossil fuels on the earth. Remember, methane is a fossil fuel. It's 1 carbon. It's not as big as octane, which has 8, but methane has 1 carbon, and you can use it as fuel. We do use it as fuel. Okay, and this is what it looks like. Okay, you have these carbon rings here, or these molecules that hold around it, these water molecules, and they form a cage around methane. When you see a black ball here, that's carbon. The white ones are hydrogens. Okay, so you have methane gas trapped in this water lattice work here. Okay, and this freezes, and it forms these huge reserves of methane fuel. So in this frozen state, these hydrogen-bound water molecules form an open lattice work surrounding the methane. Okay, so methane, which is nonpolar, okay, because it's a hydrocarbon, remember, it just gets trapped inside the space within this lattice. Okay, so frozen methane then is found on the ocean floor. It's formed by animals, decaying plant life. Okay, there are large pockets of oil and natural gas all over the earth of this methane gas that's trapped underneath the surface of the ocean. Okay, so these are what's called methane hydrate, because it's trapping with oxygen. It forms when methane from one of these pockets under the ocean seeps up through the sediments. Thank you. All right. Okay. So when the gas reaches the ocean floor, it expands and freezes. Okay. Vast regions of the ocean floor are covered by these ice fields. Huge fields of these things are available for tapping for resources, for hydrocarbon resource for fuel. So a lot of these communities of methogens, organisms that can use methane for a food source, have developed on these ice fields. So organisms that use methane to consume, okay, just like we use oxygen, have developed a certain species there on the ocean floors. They live under great pressures, extremely low temperatures, with no light. So the shape, the feature of these creatures are really strange. Because again, there's no eyes, because there's no light, and they're extreme low temperatures, extreme pressures that they're under the ocean. If you can mine these ice fields and use methane as a fuel, okay, we have a huge abundance of this in the ocean floor that we can mine. Okay. The U.S. Geology Society estimates that the amount of methane hydrate in the United States is worth over 200 times the conventional natural gas resource in the country. So you got a whole lot of untapped fuel there in these methane deposits, methane hydrates. Okay. Methane is flammable. We can burn it, just like propane, just like butane, just like any other fuel. And like carbon dioxide, it is a greenhouse gas. Okay. It's about 20 times more efficient at trapping heat than carbon dioxide. Okay. Remember one of the problems with carbon dioxide, greenhouse gas, is it traps heat in our atmosphere. It doesn't allow it to dissipate out. Methane works about 20 times greater than carbon dioxide to keep heat into our atmosphere. Use our energy is working with industry to develop ways to harvest the methane, but they got to figure out how to do it without releasing into the atmosphere. Because what's going to happen releasing the atmosphere? We already have problems with global warming already, with the carbon dioxide being released. If methane traps heat 20 times more than carbon dioxide, what's that can do in our environment? It's going to really increase the greenhouse gas effect. So if we can mine it, we got to be able to mine it safely. The government should be right. The government ever gets involved, it's always done safely. Okay, they have division of the hydrocarbons. Remember, hydrocarbons are what? Hydrocarbons are compounds that contain what?
Hydrogen and carbon.
Hydrogen and carbon.
Perfect. They contain hydrogen and carbon. That's it. You can have aliphat. There's two types of hydrocarbons. There's aromatic, which smell nice, and there's aliphatic. Okay. Aromatic compounds are your benzene rings, and we'll get into that in a little bit. Okay. It's a certain type of structure with 6 carbons in a ring and alternating double bonds. That's your benzene ring. Those are aromatic compounds, like your fragrances with fruit smells, bananas, strawberries, raspberries. Those all have these benzene rings inside of them that gives you this nice smell. Aliphatic compounds don't smell nice. Those are alkanes, cycloalkanes, alkenes, and alkynes. Okay. The difference here is alkanes have an ANE ending. Those are all single bonds. Cycloalkanes are all connected in a circle, whether there's 3, 4, 5, 6, 7, 8, and so on. Okay. Alkenes have an ENE ending. That means there's double bonds. Alkynes have a YNE ending, which means they're triple bonds. Okay. So those are your aliphatic hydrocarbons. There's alkanes, A and E is single bonds. There's cycloalkanes, which means they're in a cyclical structure. There's alkenes, which are ENE, which means double bond, and YNE means triple bond. Okay. Now we're going to talk about hydrocarbon saturation. Saturation means if something's saturated, there's as much there as possible. So if a hydrocarbon is saturated, it means there's as many hydrogens as is possible. Okay. So alkanes, okay, are compounds that contain only a carbon-carbon and carbon-hydrogen single bond. Okay. A saturated hydrocarbon has no double or triple bonds. It's saturated. If it's saturated, it has as many hydrogens as is possible, which means there's no double or triple bonds because then you won't have many hydrogen. So if you have a compound, okay, like right here, we have, this is propane. There's 3 carbons, and every carbon has as many hydrogens as possible to give it 4 bonds. Okay, this is propene, E-N-E ending. This has a double bond. Okay, this double bond means that this hydrogen and this hydrogen aren't there anymore. So it's unsaturated. It does not have as many hydrogens as is possible for the number of carbon atoms. Okay, so if you have two carbon atoms, if the compound is saturated, what's the most hydrogens you can possibly have? So 2 carbon atoms, how many hydrogens can it possibly have? If every other one,
6.
6.
Six.
Perfect. Has 6 hydrogens. Okay, that's saturated. Now, if that carbon had a double bond, how many hydrogens would you have now?
4.
4, because we 1 here, 1 here, 1 here, 1 here. So you do not have as many as you possibly could. So this is saturated. It's saturated with hydrogens. This is unsaturated because you don't have as many hydrogens there that is possible because of the double bond, or a triple bond would do the same thing. Okay. If there were 2 carbons and a triple bond between them, how many hydrogens would you have?
2.
2. Perfect. Yeah, you'd have 2, 1 on each end. That would get each carbon 4 bonds. So this is also unsaturated. Okay. So saturated hydrocarbons have as many hydrogens as possible. No double bonds, no triple bonds. Everything's filled with hydrogens. Unsaturated means you have at least 1 double bond, okay, or a triple bond, or cyclical structure. Okay, something that decreases the amount of hydrogen that can normally be attached. Okay, so that's what saturated, unsaturated mean. Cyclical structures means they form a cycle, they form a ring. So some hydrocarbons are cyclic in nature. They form a closed ring. Remember, the aromatic hydrocarbons contain a benzene ring. Look at this right here. That's your benzene ring. All these are representative. Every one of these, this is cyclohexane, but see how benzene has double bonds. These are what's called line structures. When we draw line structures, we're going to learn about in this chapter also. Okay, every corner represents a carbon atom. Okay, so every time there's a bend, every time there's the end of a line, there's a carbon atom there. So this structure has 1, 2, 3, 4, 5, 6 carbon atoms. Okay, in looking at this structure, how many hydrogens are in this cyclohexane? Anyone want to guess? How many
24.
hydrogen atoms? What's that?
24.
Not 24.
Is it 12?
It's 12. Perfect. Exactly right. Because every one of these carbons, there's 2 bonds here, right? So that means there's 2 bonds for hydrogen, 2 bonds for hydrogen. Every one of these has 2 hydrogens attached. When we draw line structures, we do not include the hydrogens. Okay, let's look at this benzene ring here. Okay, this is alternating double bonds, 6 carbons in a structure. How many hydrogens are in benzene in this structure?
6.
6, because there's 1 can be here to make 4, 1 here makes 4, 1 here makes 4, 1 here makes 4, 1 here, and 1 here. So there's 6 hydrogens. Okay. So aromatic structures contain a benzene ring. Okay, that's by definition aromatic structure. When we're dealing with a bunch of hydrocarbons, they're going to form functional groups. These functional groups are going to identify the type of compound and how it reacts and what it does. Okay. So we're gonna learn all about these different functional groups in the different chapters. You don't have to worry about them. Just introduce them right now, and we'll be learning about them in each of the chapters go into great detail. So we have alcohol as a functional group. Okay. This is a general formula for an alcohol. The R, whenever you see an R in organic chemistry, it just means a hydrocarbon group. It could be 1 carbon, 2 carbons, 3 carbons, whatever. Okay. So there's an OH group attached to carbon chain. That's an alcohol. Okay. An aldehyde. An aldehyde is an R group which attached with a C double bond O and a hydrogen. That's an aldehyde group. Okay. An amide. Okay. This is your peptide bonds and your amino acids forming proteins, which we'll go into. Your R group is attached to what's called a carbonyl group, which is C double bond oxygen, and then an NH2 group. An amino group, an amine is an R group attached to an NH2 group. That's an amine. So the difference between an amine and amide is this carbonyl group right here. Carboxylic acid is an R group attached to a COOH. Okay. An ester is an R group attached to a C double bond O, which is your carbonyl group. Another oxygen, then another R group. Okay. If this R group was an H, that's a carboxylic acid. Okay. So RCOOR is an ester. An ether is an R group attached to an oxygen with another R group on the other side. Okay. A halide is an R group attached to a halogen. Iodine, chlorine, bromine, or fluorine. Ketone. Ketone is an R group attached to what's called a carbonyl group, C double bond O, and then another R group. Alkene are your double bonds. Alkynes are your triple bonds. Alkane is single bond. Alkene is double bond. Alkyne is triple bond. Those are your functional groups. So that's in your text. And we'll be going through each one of those in great detail. Okay. So we're talking about alkanes. So ANE ending means what? There you go. What is oops, how did I got too far. What? Yeah, still went too far. What does ANE ending mean?
Single bond.
Single bond, right?
Single bond. You got it. Perfect. It means a single bond. So the general formula is CN H2N plus 2. All right. So you double the number of carbon atoms and then add 2. Because with single bond, there's no other way around it. Have my back there. Still going too far back. Computer has a mind of its own here. All right. So say we had 5 carbons. 1, 2, 3, 4, 5. This formula says we double the number of carbons because there's 1, 2 on each carbon, right? And then we add 2, 1 for each end. That's all it means. So when we have alkanes, if we have 5 carbons, we have 5 times 2 plus 2. So it'd be C5 H12. Okay. So N is the number of carbon atoms in the compound. So far, so good. All right, say I had 15 carbons in an alkane. How many hydrogens would I have?
32.
32. There'd be 2 on every carbon long and then 1 on each end. So the general formula for the alkane is CN H2N plus 2, where N is the number of carbon atoms. Okay, alkanes are saturated hydrocarbons because they have the most hydrogen atoms possible per number of carbon atoms. There are no double and no single bonds. So everything to give carbon its four structures is a hydrogen attachment. Okay. These contain only carbon and hydrogen. These are alkane hydrocarbons. And bonds are carbon, hydrogen, and carbon, carbon. That's the only bond you have in an alkane. That's a hydrocarbon. Carbon, carbon single bonds, carbon, hydrogen single bonds. Okay. Different things we use in organic chemistry. The molecular formula. We talked about that before. We talked about molecular formulas and structural formulas. The molecular formula is the number of each type of atom in a compound. So water, the molecular formula is H2O. Propane, the molecular formula is C3H8. Okay, that's the molecular formula. It's the number and kind of each type of atom in the molecule. The structural formula shows the shape of the formula. Okay, it shows you how this is 2 carbons here, and this is 3 carbons in a row. Okay, what is it called when there's the same molecular formula but a different structural formula? What's that called?
Isomer.
Isomer. Perfect. That's called an isomer. Okay. Condensed and line formulas. This is what we're going to be. Most of the stuff we use is line formulas because it's so much easier to draw. A condensed formula shows all the atoms in a molecule in a order, indicating how they're bonded. So a condensed formula will show you CH3 bonded to each other. Okay. CH3, CH2, CH3. All that means is the carbons are connected and your hydrogens are 3, hydrogens are 2, hydrogens are 3. But you condense that down into one line. So you have CH3. Okay, that's your condensed formula. When you write it out in one line, you don't branch apart. You don't show the branches. In a line formula, that's when you just draw lines. There's a carbon atom at any location where the lines intersect and at the ends. So at the end of every line or where the lines intersect, there's a carbon atom. So if I do this structure here, okay, how many carbon atoms would that be?
Six.
Perfect. Exactly. There'll be 6 carbons. How many hydrogens?
14.
14.
14. Perfect. You got it. And 14 hydrogens. Okay. But this is what's called a line structure. Okay. So the line structure with line structure, and at the ends are carbons, and each carbon is bonded to the correct number of hydrogens to make everything have 4 bonds. Okay. When we name these things, you'll be referring back to this chart many times until you memorize the names. You don't have to memorize because this chart will be provided for you no matter what exam you have with me. So don't have to memorize it, but by doing enough of them, you're going to memorize them. Okay, it's just going to happen all on its own. So this is for alkanes. Alkanes are single bonds. Okay. If there's 1 carbon, it's methane. If there's 2 carbons, it's ethane. If there's 3 carbons, it's propane. 4 carbons is butane. 5 carbons is pentane. 6 carbons is hexane. 7 carbons is heptane. 8 carbons is octane. 9 carbon is nonane. 10 carbons is decane. Okay, those are the abbreviations. Well, you're going to use those when you have attachment groups too. We're using those over and over. So 1 is methyl, 2 is ethyl, and so on. Okay, so we're using this chart to name all the different attachments as we have in carbon chain. But if it's a straight chain, if you have octane, you know there's 8 carbons. If you got an octagon, you know it's 8 8-sided figure. Okay. So write the structure and condensed formula for the following line formulas. Okay. So here's a line formula. And again, by the end of this chapter, you'll be able to say that is 2,2,4-trimethylpentane. That's that structure represent. That's a unique name. This is an IUPAC, International Union Pacific Applied Chemistry. So it's a specific name for that compound. It can only be one compound with that structure formula with that name. So let's look at this. Let's look at this line structure here. Let me get rid of some of these lines here. Okay, so this is our line structure. Okay. How many carbons are in that line structure? Nobody wants to guess?
8.
8. Perfect. There's 1, 2, 3, 4, 5, 6, 7, 8. Okay. You want to draw this the structural formula for it and the condensed formula? You have a carbon at the end right here. This one here will start right here. That's CH3. Goes to another carbon. I didn't put the line in there. Okay. CH3, there's another carbon. Okay. There's 2 carbons at, whoa. Went way too far on that one. Come back. All right. There's a carbon with 2 carbons attached to it. So there's CH3 twice, because you have a carbon here and carbon here. There's a CH2. There's a CH with another CH3. And there's another CH3. And that really is sloppy. Let me get a little bit better here. I hit done. Will that erase everything? All right. Let's get back to where we were at. Computer didn't want to do that here. All right. Now, it still came back. Trying to get rid of some of that. It doesn't like me there. All right. So look at the structure here. Okay. We're going to put everything in order. So this line here, there's a CH3. This has a carbon with a CH3 attached. This has a carbon with 2 hydrogens attached. This has a carbon with 1 carbon attached, and this has a C8 carbon at the end. So you write down the chain. Boy, this screen's acting funny on me. So we start with the first carbon, and there's 3 hydrogens with it. Then we go to the next carbon. There's 2 CH3 groups. This is bouncing all around me for some reason. Okay. So CH3 is our start. That's this point right here. Okay, go to the next carbon. There's a carbon atom, and there's 2 CH3 groups attached. Go to the next carbon right here. What's attached to that carbon right there with this mark right here?
2 other carbons.
None. Well, yeah, that's in the chain, but there's 2 hydrogens here, right?
Oh,
Because there's 2 hydrogens, so there's 2 carbons. So it's CH2. And then this carbon has 1 hydrogen, 1 CH3 group attached, and then coming down here is another CH3 group at the end. So that gives you 1, 2, 3, 4, 5, 6, 7, 8 carbons, which we have 8 carbons. Then when you read it, this is our condensed formula. All occurs on one line. It tells you there's a CH3, and there's a carbon with 2 CH3 groups attached, which these are 2 CH3 groups attached right here. Then we have another carbon with 2 hydrogens attached right there. Another carbon with 1 hydrogen attached and a CH3 group. and then a CH3 group. Okay. What you need to do for your exams is to be able to write condensed formulas, structural formulas, and line formulas, and be able to convert between them. Okay. So for a structural formula, that's this carbons. We put a carbon at every bend and at every end of every line. And then you fill it in with hydrogens. That's your structural formula. Okay. That's what the structure looks like. So you need to be able to go between line formulas, condensed formulas, and structural formulas, and go back and forth. So whether I give you a line formula or a structural formula or a condensed formula, you can write the other two for me. Okay, and we'll get plenty of practice at that right now. So writing condensed formulas, which we just did. This shows the arrows of what I basically did. This was your CH3 group, which is right here. This was your carbon, which is right there. These are two CH3 groups, which are right there. When you see parentheses in a condensed formula, it means whatever is in the parentheses applies back to this carbon. So those two CH3 groups attach to that carbon. Then we had a CH2. Then we had a carbon with a hydrogen, and then another CH3 attached to it right here. And then CH3 at the end. And here's your structural formula. And again, everything in parentheses applies back to the carbon preceding it. I know they're a little confusing, the condensed formulas, but we'll work on that a lot more too here. But you can see here's examples of condensed formulas. Okay, this is hexane. Remember back on the chart, hexane meant how many carbons? Hexane was 6. Methane, ethane, propane, butane, pentane, hexane. Hexane is 6 carbons. Okay? And that's the name of it, is in methane. If you look at when you have branching occurs, this CH3 group means this is applied back to that carbon. Okay. This CH3 group applies back to that carbon, this one to that carbon, and both of these apply back to that carbon. Come on, go back. There we go. Okay. So the condensed formula is all in a line, and it shows you when parentheses, when there's a branch, it branches off the previous carbon. And there's specific names, which end up naming all these things for each compound, each formula. All right. I remember we had methyl. Meth was 1 carbon. Methyl was 1 carbon. Methyl and methyl, all 1 carbon. Ethyl was 2. Propyl was 3. Those are the Greek numbers that we learned before. Okay. So there's hexane. Hexane should have 6 carbons. Okay. So this is your condensed formula. This is the structure formula where the lines out with bonds between them. Okay, and what's the line structure? You have 1, 2, 3, 4, 5, 6 carbons. 1, 2, 3, 4, 5, 6. That's hexane. Okay, there's a carbon at every end and a carbon wherever lines intersect one another. And there's no branches. Everything's straight across. Okay. Okay, so there's your hexane. There's 1, 2, 3, 4, 5, 6. Making sense?
Yeah.
All right, perfect. Now we got 2-methylpentane. So if you want to look at it and draw this out, there's a CH3. bonded to a CH. And look at this. This is parentheses. That means this goes back to that carbon. So CH3, that's a CH3 group. Okay, CH2, CH2, CH3. That's the structural formula for that condensed formula. Okay. Now the line formula, here's we get just a little bit trickier. The line formula has how many carbons in a straight line now, not total carbons. How many carbons are going to run? Look at this structure right here. How many carbons are in a straight line?
5.
5. So you make lines for 5 carbons. 1, 2, 3, 4, 5. And then at this one right here, the second one, there's a carbon coming straight up. So there's a line. Remember, every line is a carbon atom. So there's 1, 2, 3, 4, 5, and here's your 6th carbon. And again, at the end of a line, if there's nothing else there, there has to be 3 hydrogens. So that's your CH3 group, which is this group right here. And what the name tells you, when we're going to get into doing these naming structures, we'll give you a little preview of it right now. When you're working in organic chemistry, always work backwards. Okay? It'll make your life so much easier. So if I'm looking at the name of this thing, if I start at the end, the last word is pentane, right? Pentane means how many carbons?
5.
5, perfect. A pentagon is 5 sides. Penta means 5. ANE means what?
Single bonds.
Single bonds. So 5 carbons, single bond. There's your line. And then at the number 2 position, 1, 2, there is a methyl group. Methyl means 1 carbon. Remember, there was methane, ethane, propane. Go back and look at the chart. Methane means 1 propane. So now you know what 2-methylpropane means and how to draw it. And we'll go over a bunch of those coming up. That's not a problem. If I can get rid of all these, that would help a lot. Let's see if this goes back. All right. So 2-methylpentane. There's your line, your structure formula, and there's your line formula. Again, there's 1, 2, 3, 4, 5. And then 1 CH3 group attached to it. So this is a condensed formula. This is a structural formula, and this is a line formula. Know the difference between the 3 and how to interconvert between them. Okay. Again, we have this is our structural formula right at the top here. Okay. Remember, this CH3 refers back to that carbon. So if we're going to draw the structural formula, I have CH3. Okay. I have a CH2. I have a C8. Well, that is the structure. I'm drawing the. I need to put lines in there. Okay. So CH3, CH2, CH, and what? That line goes back to CH3, CH2, CH3. There's your structural formula. Okay.
Professor,
Yes.
why didn't you put the middle CH as CH? You like did the connection
You could.
with hydrogen.
You could put like here, like that.
Yeah.
You could do that too. That's fine.
Okay, sounds good.
Perfect. Yep. Either way is fine. Sometimes draw it out to make it a little bit easier to see where the bonds are. And then to do the line structure, how many carbons in a straight line?
5.
5. So 1, 2, 3, 4, 5. And then at the 1, 2, 3 carbon, there's a CH3 group. That's the line structure. Okay. We'll be able to do that from the name. Look at the name. Pentane. All single bonds, 5 carbons. At the third one, there's a methyl group. But methyl is 1 carbon. Okay, so that's how we're naming these. So there's the structural formula broken out, and there is the line formula. Okay, let's do 2,3-dimethyl. That just means di means 2. Okay. So if you want to write, this is the condensed formula. Structural formula would be CH3 connected to what? What's it connected to?
CH.
CH, and then a CH3, right?
Mm-hmm.
That's this one going right to here. And then another CH, and another CH3. That goes to there, and then CH3 at the end. That's your structural formula. Okay. Get rid of some of my drawings here so I can see a little better. All right. So here's your CH3. That's the CH3 right here. Here's your CH3. That's that right there. Here's your CH3. That's that right there. And there's your CH3. Okay. That's how you convert from a structural formula to a line, to a condensed formula, or from a condensed formula to a structural formula. Okay. Now, how would you do the line formula? What's the longest, what's our straight line? How many carbons?
4.
4. Perfect. So you would draw 1, 2, 3, 4. Okay. And there's a CH3 group at the second and third carbons. So you make a line and you make a line. That's what it looks like. That's 2,3-dimethyl butane, because there's 4 carbons. And there's the line structure. Okay. And I think there's one more. The other we'll take about a 10-minute break here. Almost time. All right. So look at this one here. This is what type of formula does this represent? Which one of the 3?
Condensed.
Condensed. Perfect. That's a condensed because it's all on one line. And everything's squished together. There's no division, no bonds between them that are showing. That's a condensed formula. Okay. So we start with the CH3. That's this right here. Right? Then we got the next, we have a carbon. Line, carbon. And that carbon has 2 CH3 groups attached to it. 1, 2. Okay. That takes care of these right here. Then we have a CH2. That takes care of that. And then we have a CH3. And there's your structural formula. We got a question in chat that says, why do we not separate the H's? Just because I'm lazy. You could just as easily write it this way for CH3. But when they're at the end, when they're at the end, I just put CH3. There's no difference. You would not be marked wrong if you put all these CH3s like that. Okay. So either way is fine when you're doing structural formulas. So now the line, if we did that, okay, let's look at the line formula. So here's the structural formula. If I can get some of those lines to go away here. We're good. There we go. There's our structural formula. Whoops, what happened here? Oh, that was our. There we go. Okay, so here's our structural formula. Again, the CH3, two CH3s attached to a carbon, CH2, and a CH3. That matches all of those. Our line formula. How much are, when we draw our first line, how many carbons are we going to represent?
4.
4 carbons. So it'd be 1, 2, 3, 4. And so there's your CH3. At your second carbon, there's going to be 2 CH3s attached. So there's 1 CH3. There's a second CH3. And that's it. That's what your line formula would look like right here. Okay. 4 carbons. There's number 1, number 2, number 3, and number 4. Okay. At the second carbon, this right here, at the second carbon, there's going to be 2 CH3 groups. One here and another one here. We just talked about the different ways carbon bonds to hydrogen, making the different structures. So carbon, when there's 4 bonds to it, is always going to form a tetrahedral structure. Tetrahedral just strictly means there's 4 bonds attached to it. And everything's isolated about 109.5 degrees. That's according to the VSEPR theory, valence shell electron pair repulsion. Okay. These are different representations of our 4 bonds to carbon. Okay. That's a ball and stick model. And you can see in 3 dimensions, this is coming out, that's going back, and that's in one plane. Okay. So you have a Lewis dot structure. You have a tetrahedral shape around the carbon. You have a drawing with dashes and wedges to represent 3-dimensional structures. Okay, or a stick drawing of it, or a ball and stick model of it. All those are different ways to represent the exact same thing of the tetrahedral shape that carbon takes on. Okay, and that's what it is. If we were in class, you could do these little models here, and you'd have whenever you have a black ball that represents carbon, and the white represents hydrogens. But that's a tetrahedral structure. Every one of these angles that you see here, let me get one that's going to show a little better purple. That angle, that angle, that angle, that angle, the angle between these two in the back here from around behind here. Every angle, if you measure it, is 109.5 degrees. Everything is exactly the same. Okay, drawing methane and ethane. Okay, this is how you draw it. One comes out of the board, one goes into the board. That's a 3-dimensional structure. Methane is 1 carbon. Ethane was 2 carbons. Okay, but everyone here, every carbon with 4 bonds, no matter how many carbons attached to it, are going to have a tetrahedral structure, and they're going to rotate in 3-dimensional space. Okay, this is called a staggered form because the hydrogen molecules, again, are going to interface with each other. They'll either line up or they'll stagger away from each other, which is more stable. Okay. Now we can have ethane and we can have butane. Ethane is 2 carbons. Butane is 4 carbons. Okay, and there's our 109.5 degrees. Here's our 2 carbon. This is ethane, and that's the ball and stick model of ethane. And you'll see it's a staggered formation. You'll see this hydrogen and this hydrogen from a V, and this one's straight up between the 2. So it's not going to stereochemically inhibit one the other. Okay. Now butane has 4 carbons. Every one of those is 109.5 degrees. And you'll see how that staggers with the ball and stick model. Okay. You see how you have your 2 hydrogens split and then the one in between it. You'll see how this is out of the way for each one as they stagger. They don't fold back up close to each other. You see the 2 down here, 2 up here. See 2 up, two down, two up, two down. That way the hydrogens are staggered. They're not interfering with one another in the structure.
Professor,
Yes.
what does the wedges mean? Does that just mean that the hydrogens are closer together, or?
No. Everything's 109.5 degrees. Everything's the same distance apart. It means it's
Mhm.
out of the paper at you or out of the screen. The dashes are going back into the screen. It's trying to make it a three-dimensional image.
Oh, okay.
So it's if you're looking at it, it's this dash right here is sticking out towards you. This line's going backward is going back into the screen. So it's like popping out or being behind, making a three-dimensional image out of it. In other words, if right here, these are the lines right here, these two. This is coming out. This is your wedge. This is going back. That's your dashes.
Oh, I see what you're saying. Okay.
It's the representation of a three-dimensional image. Does that make sense?
Yeah.
All right, good, perfect. All right, so isomers. Isomers by definition were the same molecular formula, different chemical formula. Different structural form, sorry. Same molecular formula, different structural formula. Okay. So a lot of carbon compounds exist as these different isomers. Okay, same molecular formula, different structural formula. Okay, so if we look at C4H10 like we did before, we could put them all in a straight line, all four carbons, or we could branch one of the carbons. Okay, both of those are C4H10, but they're different. So they have to have different names. This is butane. Again, butane meant four carbons. This is methyl propane. Propane is three carbons, and a methyl group is one carbon. Okay, and we'll learn those names in just a little bit here. Okay, if you look at the different isomers, they'll have different physical properties. Compare the basic Lewis structure of hexane. Okay, there's four isomers of hexane. Hexane is 6 carbons. Okay, from that chart. Have one or more carbon atoms branching from the main chain. Branch chains for a molecule has much smaller surface area. Okay, because it decreases the area that's allowed to react. The intermolecular forces are weaker. Okay, so if you have a carbon chain, so 1, 2, 3, 4, 5, 6, and we start branching them 1, 2, 3, 4, 1. I don't want to do that. Let's compare this 1, 2, 3, 4, 5. There's 6 carbons. 1, 2, 3, 4, and let's put some branches on it over here. Okay, if you look at those, they're the same number of carbon atoms. Okay, but this has a smaller surface area, so there's less forces between them. Okay, so the intermolecular forces are weaker as they branch because you don't have those long chains that can tend to stick together. Okay, so boiling points and melting points are lower than straight chains because the intermolecular forces are weaker. So this one here is going to have a lower boiling point than hexane here, even though it's the same number of carbons, same number of hydrogen atoms. Okay, so let's look at the different isomers. 1, 2, 3, 4, 5. That's hexane. Okay, you can branch there. You can branch at the third one. You can have 2 branches there, or you can have 2 branches all in the same one. All of these isomers have the exact same formula of C6H12. Okay, you can count any of those up. C6, I'm sorry, C6H14. I was going, wait a minute, that didn't sound right. Sorry about that. C6H14. I'll have 6 carbons and I'll have 14 hydrogens. They just arrange differently. So they're isomers. Okay. This one has a methyl group, a CH3 group at the second carbon. This one has a methyl group at the third carbon. This one has a methyl group at the second and third carbon. This one has 2 methyl groups, both at the second carbon. Okay. Now, don't forget, if we drew the CH3 groups over here, it'd be the same thing because these can rotate in three-dimensional space. Okay, so if I put these CH3 groups over here, it'd be the exact same thing because you just spin it around. Okay, so that doesn't count as an isomer; it's the same compound. So you got to be very careful when you're doing these that you realize these are what I do in 3 dimensions here. You got to remember they can rotate in 3-dimensional space. Okay, so there's the 5 different isomers of C6H14 or hexane. Okay, there's no other possibilities to do it with. Okay, because we're gonna have to remember how the longest hydrocarbon chain is and how they can rotate in 3-dimensional space to make sure we don't duplicate when we're doing isomers. Okay, just like we showed with before, this is the same thing, C6H14, and it's isomers, same molecular formula, different structural formulas. Because they're different structural formulas, are different physical properties. The more branches it has, the lower or the weaker the intermolecular forces are. Okay, because that branching decreases the surface area available for the London dispersion forces. Okay, so we look at hexane going down to 2,2-dimethylbutane, and we see the boiling point decreasing and the melting point decreasing. It gets lower. Okay, there's less holding it together as you get those intermolecular forces weaker because of that decrease in surface area. Okay, so our physical problem we've been talking about, we're still talking about alkanes and they're hydrocarbons, so single bonds. They're non-polar molecules. There's nothing making those polar. They're not water soluble, okay, but they are soluble in non-polar solvents. They have low melting points. They have low boiling points. Okay, they're usually less dense than water, lighter than water. Okay, as the molecular weight increases, the melting point and boiling point also increase, and along with the density. Okay, so if you had a compound C6H14 and another one that was C30H62, which one of these, this is number 1, this is number 2, which one would have the higher melting point?
C30H62.
Perfect. Exactly, because there's more things to bond to it, more things to hold together. Those intermolecular forces are stronger. Okay. What? Okay, so as the molecular weight increases, you see the boiling point increases, just like we showed, because there's more surface area for those to stick together and increase those intermolecular forces. Melting point's the same way, not as drastic, but you still see that increase as the number of carbons increase. So as your carbons increase, which is along this line here, your temperature or your boiling point and melting points both increase. Okay. So most alkanes are what's called hydrophobic. Hydrophobic literally means in Latin, water hating. They can be 2 things. They can be hydrophilic, which is water loving, which are your polar compounds, or they can be hydrophobic, which is water hating, both in Latin. Okay. And you know why we use Latin for these terms, right? Who's had my classes before? We use Latin for anatomy. We use Latin for chemistry terms because Latin is a dead language. It doesn't change. Okay, so we can use it to reference different things. Okay, there's not a country in the world today that speaks Latin. Okay, so it never changes. I mean, English changes every day, literally. I mean, terms like BFF, LOL, that meant nothing when I was growing up. You know, English changes tremendously. Well, Latin is a dead language, so that's why we use it for a lot of reference into things. It's not going to change on us. I mean, terms changed tremendously. So most of your alkanes are hydrophobic. It's going to be real important when you're getting into biochemistry in dealing with enzymes and chemical properties of these things as they're relating to how they bond together. DNA, RNA, they have hydrophobic, hydrophilic range of things. So hydrophobic is water hating, most of the alkanes, because they are non-polar. Straight chain alkanes comprise a homologous series, which is a series all the same as they're all straight chains, the same functional class that differ by a CH2 group. In other words, methane, the difference between methane and ethane is a CH2 group, an extra carbon. The difference between methane and propane is 2 CH2 groups. Difference between methane and butane is 3 CH2 groups. Okay, it's a homologous series as these carbons increase. Non-polar alkanes are insoluble in water because water is polar. Okay, or any other polar solvent. Okay, alcohol is polar. Okay, these non-polar alkanes are not going to be soluble in alcohol or water for the same reason. Okay, they're less dense than water, so they'll float on top of the water. So carbon classifications. Carbon, when it bonds or when it's straight lines or branches, it has different effects, different properties. So carbon atoms are classified according to the number of carbon atoms to which they're attached. Okay, a primary carbon, that's this one here, has 1 carbon attached to it. A secondary carbon has 2 carbons attached to it. And a tertiary carbon has 3 carbons attached to it. So you got primary, secondary, and tertiary. And what you're going to see on your exams, you're going to see a structure. I'm going to put A, B, C, or you have to put how many carbons are secondary, primary, or tertiary. Be able to identify them. Okay. So classify. Here's your compound. Classify each of the carbon atoms in the following structures, either primary, secondary, or tertiary. This carbon here, is it primary, secondary, or tertiary?
Primary.
Primary. That's a primary carbon. There's only 1 carbon attached to it. This carbon, primary, secondary, or tertiary?
Secondary.
Secondary, perfect. Okay. There's 2 carbons attached to it. This carbon is what?
Secondary.
Secondary. And this carbon?
Primary.
Primary. So the test question would typically be a multiple choice. How many primary carbons are in this structure? And you say 2. Okay. So there's your primary carbons. There's your secondary carbons. Okay. This structure, classify each carbon. Let's take this one here. Primary, secondary, tertiary.
Primary.
Primary. There's 1 carbon attached. This carbon.
Tertiary.
Actually, that has 4 carbons attached.
Oh.
So that actually breaks the rules. That's a quaternary. There's primary, secondary, tertiary, or quaternary in this case. Because that one has actually 4 carbons attached to it. And this one here. Would be what?
Primary.
Primary.
Primary. And this one here.
Primary again.
Primary again. And this one here.
Primary.
Primary again. Perfect. So all 4 of those outside are primary. And the one here, this one's a tertiary. That has 4 carbons attached. Okay, that's usually how to identify those. All right. A couple more here. Let's start with this one here. What is that?
Primary.
Primary. This one here.
Primary.
Primary.
This one here.
Tertiary.
Tertiary. That has 3 carbons attached. This one here,
Tertiary.
Tertiary.
perfect. This one here,
Primary.
Primary.
primary. This one here,
Secondary.
secondary. And one more,
Primary.
primary. Okay. So the question would be, how many secondary carbons does this compound have? You would select the answer 1. Okay, so there's your primary carbons. There's your secondary carbon. And there's your tertiary carbons. All right. Classify each carbon in the following compounds as primary, secondary, or tertiary. Now it's not so easy, huh? Now you got to figure out what the drawing looks like. You got to figure out the structure formula from the condensed formula. And then you could do the problem. So let's figure it out. Okay. You should all be able to draw the structural formula for that. You have CH3 bonded to what? CH2 bonded to C. Now this C has 2 CH3 groups attached to it. If I hit my hand on it, does it sometimes on the iPad? Okay. So that has a CH3. That has a CH3, right? There's your parentheses. And always when you see parentheses, it refers back to the previous carbon. And then you got a CH2. And then a CH3. Now you can identify your carbons. So if we look at this structure, how many secondary carbons are in this structure? You could have 0, 1, 2, 3, or 4. What would your answer be? The number of secondary carbons.
2.
Very good. Perfect. There's 2 of them. Secondary carbons are right here and right here. By definition, secondary carbon has 2 carbons attached to it. How many primary carbons are there?
2.
More than 2.
4.
There's 4. Perfect. This is a primary. This is a primary. This is a primary. And that's a primary. Okay. That's all the, I know it makes a, see if I can get some of this out of the way here so you can see the answer pictures here. Sometimes I scribble too much on these. There you go. Be able to see some of these now. So there's your structure all drawn out. Little neater than I draw it out. I won't go back anymore. Okay. But each of the red dots is a primary. Each of the blue squares is a secondary, and the green triangle is a quaternary. Okay. There's another one. And again, you have a CH3 group, CH2, CH2, CH2. So there's your line. Then you have a carbon with a hydrogen, and this CH3 group attaches to that hydrogen. CH3, and then CH3. Okay, so you would draw it out, and that's what it would look like. There's your CH3, CH2s, and there's your 2 CH3 groups attached to the long chain. So you have 2 primary carbons. I'm sorry, 4 primary carbons, 1 at each end of the long chain, and 1 at each end of the methyl groups that are attached. Right? Then you have 3 secondary carbons. Each one of these carbons has 2 carbons attached to it. So those are secondary. And you have 2 tertiary carbons. Each one of these has 3 carbons attached to it. Making sense?
Yep.
So far, so good. Good. All right. Alkyl groups. All right. Alkyl groups are the carbon, like, excuse me, the alkane carbons, but their attachments. They're called substituent groups or alkyl groups. The only thing we do, we drop the ANE ending and add YL. Okay. So if it was ethane, ETHANE, we drop the ANE and it becomes ETHYL. Ethane was 2 carbons, right? Okay, so we drop the ANE, YL. So that means we're attaching 2 carbons to the chain. That's ethyl. If it was propyl, propane, drop the ANE, change it to YL. If we have a propyl group, how many carbons are we attaching? Propane was 3 carbons. So propyl is a 3-carbon attachment. Okay, remember that chart? Methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, and decane. Those are the first 10. And we get longer ones, we do the fatty acids. Okay, so an alkyl group is an alkane with 1 hydrogen atom removed. So this is methane, CH4. So methyl would be CH3 with an attachment. We drop one of the hydrogens and make an attachment to the carbon chain. So this is methane. We drop one of the hydrogens. So now this can attach to a carbon chain like an argon or something, and it becomes methyl. We drop the ANE, we add YL. And we drop one of the hydrogens for our group. And the number of carbons in that attachment is going to be represented by the name from the chart: methane, ethane, propane, butane, pentane, etc. Okay. Ethyl groups. Ethyl groups have 2 carbons. So for ethane, all 6 hydrogens are equivalent. We remove 1 hydrogen, and that generates the ethyl group. So this is ethane, 2 carbons. We drop the ANE and add YL. Okay. So we can attach here, we can attach here, or we can attach it there. Oops. Okay, because it doesn't matter which hydrogen we drop. We're attaching 2 carbons to that chain. Okay, so names and formulas of the first 5. Come back here. Where were we at? Right there. Okay, so we have 1 carbon as a group attached. This is methyl. 2 carbons attached is ethyl. 3 carbons attached is propyl. 4 carbons attached is butyl. 5 carbons attached is pentyl. Okay. Those are our attachments. Okay, so alkyl groups are classified according to the number of carbons attached to the carbon atoms that join it. So all continuous chains are primary attachments because there's only 1 carbon attached to it. We can have isopropyl and sec-butyl are secondary groups. Okay, all that means is this is our primary group where 1 carbon attaches. If we have 2 carbons attached at each end, that's our secondary alkyl group. Just like primary, secondary, tertiary carbons. Okay, if we have 3 groups attached to the carbon, that is a tertiary alkyl group. Alkyl group is just the grouping of carbons, lost a hydrogen, and it attaches to the chain. Okay, we can have isoalkyl groups. Like in propane, if you remove the hydrogen, you can do it from 2 different propyl groups, depending where it is, from either from the end or from the middle. If we remove the hydrogen from the middle carbon, it's going to attach in the isopropyl position. It'll be isopropyl. Okay, if we remove the hydrogen from the end, it's just going to be a propyl group. Okay, So we can have propyl or we can have isopropyl. Everybody see the difference? Propyl group, we're taking the hydrogen off from the end and attaching. Isopropyl, we're taking the hydrogen off from the center and attaching it. So it's going to be an isomer. It will be different depending if we use the isopropyl or the propyl group. Everybody see the difference? Yeah, okay, perfect. Okay, so again, propyl group, we're taking off one of these hydrogens. Isopropyl, we take off one of those hydrogens. Okay, sec alkyl groups. That was iso, these are sec. Butane, okay, gives two butyl groups, depending when you take out a primary or a secondary hydrogen removed. So here's butane. Okay, butane, if we take off one from the end, we get our butyl group. Okay, if we take off one from one of the middle ones, we get a sec butyl group. So it'd be sec butyl, whatever the long chain is, or butyl group. So butyl, you take off the hydrogen at the end. Sec butyl, you take off the hydrogen from the secondary carbon. And whether I take it from this carbon or this carbon, it's exactly the same. Because you just flip it around three-dimensional space and it becomes a second one. Okay, so that makes no difference. Just like if I take it off this side or this side, makes no difference. Because it's going to rotate in three-dimensional space. Okay. So remember, you got isopropyl, isopropyl and sec butyl are the two ones because of the different arrangements of the carbon atoms. Okay. You can have isobutane if we have the methyl group right in the middle. Okay. That's a propyl group with a methyl attached. It's also called isobutane because it goes right between the middle of it. So you can have an isobutyl group where it comes off the end, or a tert butyl group where it comes off the middle of that. Because now you got a tertiary carbon. Okay. So this is a little exception to the rule. Okay. You can have like I said, the isobutane, it's the name of this compound, right there. If you take the hydrogen from the end, it's isobutyl. If you take the carbon from the middle group here, it becomes tert butyl because this is a tertiary carbon with three other carbons attached when you take the hydrogen off. And it doesn't matter if you take the hydrogen from here, from here, from here, or either of those ends, they're all the same. Again, because it rotates in three-dimensional space. Okay. So those are some of the namings we have. So you got isopropyl. You can see where it's attached, how that. Isobutyl, sec butyl, and tert butyl. Okay. The four different types of branched alkyls you know as different types of attachments. Nomenclature. How are we going to name all these things? Get my computer over here. There we go. Okay. We use what's called the IUPAC nomenclature, International Union of Pure and Applied Chemistry. That's who's responsible for naming all these hundred thousands of organic chemicals. Okay, so before learning all the names, okay, all the structures of the eight alkyl groups must be learned. Okay, the alkyl groups are historical names accepted by the IUPAC and integrated into modern nomenclature. That's what we use when we're naming them. So the alkyl groups, we use methane, which is methyl, ethyl, propyl, butyl, pentyl, hexyl, heptyl, octyl, nonyl, and decyl. Okay. And we get them from methane, ethane, propane, etc., going down the line. Okay. For 11, 12, 13, and so on up to 20, we use undecane for 11, dodecane for 12, tridecane is 13, tetradecane is 14, pentadecane is 15, hexa, hepta, octa, nona, those are all the same. And we just put that in front of decane. Decane is 10. Tetra is 4, so that's 14. Okay. Octa is 8. Deca is 10. That's 18. That's how you get those names. Okay. So the base or parent name for an alkane is determined by the longest carbon chain That's how you determine the name. We find the longest carbon. Doesn't matter if it's bent. It could be written, if it's written like this, CH3, CH2, 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 CH3, CH3, CH. Okay. The longest carbon chain is not 1, 2, 3, 4. The longest carbon chain is 1, 2, 3, 4, 5, 6. So there's your longest chain. The longest chain does not have to be straight. Oops, put my computer in. Okay. Sometimes it is, but a lot of times it's not the straight chain. So the first step in naming these compounds correctly, okay, is to find the longest carbon chain. The longest chain may bend and twist. Okay. Any carbon group not part of the base chain is called a substituent. Okay. So if you have a 1 carbon that's not part of the base chain, okay, that's a methyl group, and we're going to name it as such. If you got a 2 carbon chain that's not part of the base chain, it's an ethyl group. If you have a 3 carbon chain that's not part of the base chain, and they're 3 in order, it's a propyl group. Okay, these are substituent or alkyl groups because you've dropped the A and E and you've added YL. Okay, so rule number 1, you have to do these in order, or they're not going to make sense. So rule number 1 of naming these things is to find the longest chain. Okay, let's look at this one here. What's the longest possible chain you can find? One, 2, 3. Okay, if I went up, that'd be 4, 5, 6, but that's not right. So 4, 5, 6. That's actually not the longest chain. Even I'm doing it wrong. 1, 2, 3, 4. Because the other way would put a 3 right there. So it's going to be longer that way. 5, 6, 7, 8. So it's an 8 carbon chain. It's all single bonds. So it's octane. That's what A stands for. There's a substituent attached here. There's a substituent attached here. This is a methyl group. This is an ethyl group. Okay. So you have 2 substituents attached to an 8 carbon chain. The next one's a little bit easier. 1, 2, 3, 4, 5, 6, 7. And the substituent is a methyl group. 1 carbon group at the number, that'd be the 3rd carbon. Yeah. Okay. So number the atoms in the carbon chain from the end with the first branch. Okay. So you continue to come point, it comes back. In other words, you start with 1, 2, 3, and you got a branch right here. 4, 5, 6, and a branch right here. Okay. Now look at, why didn't they start with this one as number 1? You number that. Once you find the longest chain, you number it. So you give the substituent the lowest number possible. So starting numbering from here, we have 1, 2, our first substituents at number 3. If we would have numbered the other way, we would have put 1, 2, 3, 4. Our first substituent would be at number 4. The lowest number gets precedent. So we always number the longest chain, and we make the substituent the lowest number possible. Is that making sense? Sort of. I know it's a lot of new information to throw at you here. But if we went, okay, 1, 2, 3, there's your substituent. If I numbered here, it'd be 1, 2, 3, 4, 5. 3 is lower than 5. So we number it right to left. Okay. So if we did, let's do line structures here. If I clear that screen, I still got writing material here. Okay, so here's a line structure. 1, 2, 3, 4, 5, 6. Okay. What's the longest chain? How many carbons? Here's your longest chain right here. 1, 2, 3, 4, 5, 6 carbons. Are we going to number it right to left or left to right?
Right to left.
Perfect, right to left, because that would give this substituent the lowest possible numbers. This would be 2 and 3 rather than 1, 2, 3, 4, and 5. You got it, perfect. Okay, so we're skipping something here. There we go. Okay, write each of the branches in alphabetical order before the longest chain. Like I said, we work backwards. So we're going to write everything's going to be in alphabetical order. Okay.
I was gonna pause it and I realized it's a real class. What's going on?
What's that?
Fucking cactus thorn in my hinky. It's
Okay.
like right above the knuckle.
All right.
You can see that
So we write each of the
There.
branches in alphabetical order.
the side.
You got it.
Do that.
Enjoy.
So halogens usually come first, which is chlorine, bromine, iodine, or fluorine. And then we write in alphabetical order, methane, ethane. So ethyl will come
I think
before.
this ends at 8:50. I can't remember.
Let's see who's trying to see who's unmuted here. Ah. Okay. All right. So we're good so far with that. So everything gets numbered. So the lowest possible number, and then the halogens come first in alphabetical order when we're writing them. You indicate the position of the branch on the main chain by prefacing its name with the carbon number to which it's attached. Once you number the chain, we tell you where it's at. You separate numbers and letters with a hyphen. You separate numbers with commas. And that's all the rules. I know it sounds like a lot and a little confusing, but I'll show you how we do it. Let's do one example here with a couple. Maybe let you go a little bit early tonight. We'll see how much we get going here. All right. So what the first step is to find the longest carbon chain. Okay. How long is the longest carbon chain?
Seven.
7. Perfect. Are we going to number left to right? Are we going to start on the left or are we going to start on the right?
Right.
Perfect. Start on the right. So we got 1, 2. I think we just. Okay. So we start on the right and we go across, because that way this substituent is at number 3. If we did it the other way, this would be 1, 2, 3, 4. That substituent we had 5. So there's our numbering system. Okay. What number? What's the name of the substituent? What is this thing called? It's 1 carbon. Drop the A and E and add YL.
Methyl.
Methyl. Perfect. And it's attached to what carbon? Okay. So this is our methyl group and it's attached to the number 3 carbon right there. So the name for this thing would be 3-methyl. And what's 7? heptane. That's the name. That's 3-methylheptane. There's a methyl group at number 3, carbon. There's 7 carbons, and they're all single bonds. So that's how you do it. I told you in organic work backwards. It's a lot easier. So this is heptane, all single bonds. At the number 3 carbon, there's a methyl group. And it would be in alphabetical order if we had more than one, or it'd be a halogen if one of the halogens there and it came first. Okay. So write each of the branches in alphabetical order before the base name, just like we did. Halogens will usually come first when you name halogens, then everything else is in alphabetical order. You indicate the position of the branch on the main chain by giving its name and the carbon number to which it's attached. That was our 3-methyl group. It was attached to the 3rd carbon. Okay. You separate numbers and letters with a hyphen. You separate 2 or more numbers with commas. Okay. So there's our methyl group. There's our 7 chains, our 7 longest carbon chain. So it's 3-methylheptane. Okay, tells you at number 3, there's a methyl group and heptane, 7 carbons, all single bonds, ANE ending. All right, who wants to try that one? What's the longest carbon chain? Oops, I think I'm going. It tells you above there's 8, right? 8's your longest chain. No matter how you look at it, you get 8 is going to be the longest chain that you have. Okay. Are you going to number it from the right side or the left side? What do you think?
Right.
Right side. Perfect. We're going to go 1. There we go. This computer's acting up tonight. Okay. There's your 8 carbons. There's 1, 2, 3. Here's your substituent group. That's an attachment. And this is an attachment. Okay. Everything else is part of the longest chain. It's part of the parent chain. Okay. So if we label the other way, this would be 1, 2, 3, 4. Label this way 1, 2, 3. So this way there's an attachment number 3. The other way would be number 4. The lowest one is 3, so we label it from the right side. There's 2 groups attached. What's this group called right here? It's 1 carbon.
Methyl.
Methyl. What's this group called here? There's 2 carbons.
Ethyl.
Ethyl. Perfect. So working backwards again, look at our chain. We have 8 carbons. 8 carbons is what name?
Octane.
Octane. And they're all single bonds, right? So A and E is single bonds. Octane means 8. So that's your parent chain. At number 3, there's a methyl. At number 5, there's an ethyl. Let me put it together. Okay, alphabetical order. What comes first, ethyl or methyl?
Ethyl.
Ethyl, right? Yeah. E comes before M, right? Oh, come on. Get my chain back there. So we put this whole name together. Ethyl comes first. So 5 ethyl. Why is it not marking on here? 5 ethyl. Okay. And a dash goes between letters and numbers. So 5 ethyl, 3 methyl octane. That's the name. This is an L, not a 1. That's an L. There we go. So it's 5-ethyl, 3-methyl octane. So working backwards, it's an octane, which means there's 8 carbon chain. At number 3, there's a methyl group, which is 1 carbon. And number 5, there's an ethyl group, which is 2 carbons. Okay. So we do the base name. Halogens come first. Indicate the position of the branch. Okay, by its name with a carbon number that's attached to. We say where it's attached. Okay. And then we separate numbers and letters with a hyphen. There's always a hyphen between numbers and letters. And then when we have numbers connecting to each other together, we separate them with a comma. Okay. And like I said, 5-ethyl, 3-methyl octane. And make it easy. Okay. Always work backwards. Okay. 8 carbon chain, all single bonds. At number 3, there's a methyl group. At number 5, there's an ethyl group.
Yeah, for 20 minutes.
Okay. So here's your alkanes. This is, again, this is 6 carbons. So why are we starting on the right side versus putting our 1 on the left side? Anybody know?
So your methyl group starts on the second carbon.
Perfect. If we did it the other way, it goes 1, 2, 3, 4, 5, 6. If we did it that way, our first substituent or attachment would be at number 3. Doing it this way, our first substituent attachment is at number 2. You always give the lowest number to the attachment, to the first attachment. So looking at this thing, we have 6 carbons. Okay. So what is working backwards? What's the root name of this thing going to be? What's the name for 6 carbons?
Hexa.
Perfect. Hexane. So this is hexane. And again, hex means 6. ANE means it's all single bonds, which it is. So it's a hexane. And there's 2 groups attached. There's a number 2 group. There's what? A methyl. And then number 4, what's 2 carbons?
Ethyl.
Ethyl.
Ethyl. Perfect. So there's a methyl group at number 2 carbon. There's an ethyl group at number 4 carbon. Right? And it's a hexane. So put them together. Which comes first, ethyl or methyl?
Ethyl.
Why?
Alphabetical.
You got it. Perfect. So it's going to be 4 ethyl, 2 methyl hexane. Okay. So here's your hexane, 6 carbons, all single bonds. At the number 2, there's a methyl. At the number 4, there's an ethyl. You got it. All right, let's do this one, then we'll call it quits for the night. There's been a lot of material thrown at you guys. And this is a complicated one. Oh, I didn't mean to do that. It won't go back. Oh well. If you look at this one here, the longest carbon chain that you can come up with is going to be right through here. Is going to be 9. No matter where you draw your continuous chain, you can't get longer than 9. Okay, and we have 2 substituent groups. We have a CH3, which is tertiary, a secondary carbon there, and a secondary carbon here. Okay, so we need to name those groups. So 9 is what? Okay, 9 is no name. Okay, so there's your 9. A and E, they're all single bonds. At number 5, we have sec-butyl. Okay, we're going to attach this to the secondary carbon of the butyl group. And we did the isopropyl, isobutyl, sec-butyl. Okay, This is our sec-butyl group. There's 4 carbons and attached to the second one. Okay. And this is our isopropyl group at the number 4. Okay. So it's no name, 9 carbons. Okay. And there's 5 sec. My computer's really acting strange. I think it's. I don't know why it's doing this. Wow, it's went back to a bunch. All right. Let's get back to where we were here. It's skipping slides on me. Here we go. No, that's not where we're at. Right there. All right. Okay. So here's our no name. I lost my ability to write on my computer too. There we go. It's still not doing it right. All right, computer's having trouble. So we'll finish up on this one here. But you see the nine carbons. Okay. So here's your longest carbon chain. Okay. This is a substituent group. This is a substituent group. This is sec-butyl. Okay, 4 carbons, and you attach to the secondary carbon with the hydrogen that was removed. And this is isopropyl, 3 carbons. So it's number 4 isopropyl, 5 sec-butyl. And you end up with okay. There we go. Get that back online. I get the need to stay here. Okay. Boy, this thing's acting up really strange here. All right, everybody see the 9 carbons? They see the attachment number 5 and the attachment at number 4. And we should be able to put the name up here as 5 sec-butyl. This is number 5 carbon. Okay. This is number 4 carbon isopropyl, and then no name. So 5 sec-butyl, 4 isopropyl, no name. Dashes between numbers and letters. There's commas if the numbers occur together.